Swayam Prabha. Digital India. Educated India.
So we'll do a bunch of algorithms here, a couple of algorithms here, okay? And these algorithms will be a little different in taste, that they won't really be driven by an objective function, right? And the primary reason for that is we don't know. We don't know how to write this in terms of objective function yet. There is some recent work that I'll point you to. If you're interested, feel free to look that up. But it's just that there has not been enough work on hierarchical clustering to sort of make us understand this, okay? Okay, so what we'll do is something known as an agglomerative clustering. What is an agglomerative clustering? Here is what, it's sort of better understood through pictures. So suppose the data points are like this. Say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So suppose we say, let us connect 1 and 2 together. 1 and 2 at the closest pair. Let us put 1 and 2 together. So I'm creating a tree here. The next closest pair may be 6 and 7. Okay. But now notice something has happened. When I've put 1 and 2 together, I have created a cluster, right? But now, how do I measure how close 3 is to this cluster of 1 and 2? How do I measure this distance? Depends on the? Depends on the business logic. That's a more that's a nicer answer. Are you? Never mind. Thank you. That is depends on the business logic, because all of these are reasonable solutions. You could take mean. You could take mean as in MEAN. You could take mean as minimum. Or you could do other things also, and we'll see how to do other things also. And based on that, the clustering will be a little different, right? So one solution would be that to say that, okay, I represent this cluster as an average point, and then I take the distance of this to the average point. Another could be that, okay, I look at 3 and then I say that, okay, what is the closest point in this cluster, this 1, 2 cluster to 3? Maybe it's the point 1. Right? So then the distance of the point 3 to the set 1, 2, right, is really the distance of the point 3 to point 1, right? Because that is the minimum, right? And so suppose we do this. Suppose we take this second definition, right? Then maybe I'll say that, okay, then 3 is here. Then the next clustering is this. Then the next clustering may be that you put 9 and 10 together. Then the next clustering may be that, okay, this representation of cluster and this and this cluster should be merged. Then maybe that this cluster and this cluster should be merged. Something like this. Okay? I mean, I sort of did it roughly, dropped a few points, but you get the idea. So what are we getting? We are getting a tree, right? We are getting a tree here, right? So, and what does each node in the tree represent? Each node in the tree, sorry? Each node in the tree represents a cluster. It represents, so this node, for instance, represents the cluster 1, 2, 3, 6, 7. Right? And this node represents the cluster 6, 7. So the original points are all in the leaves. Important to remember. Original points are all in the leaves. Okay, so so now let us look at these different variants and let's see what happens. Okay, so before we do this, this is the algorithm that we came up with, right? The basic intuition is that we'll keep merging the closest set of data points, build large clusters out of smaller ones, right? And the way to implement it is that you sort of keep a current list of clusters. You initialize it by saying that every point is in its own cluster. And while the number of clusters is bigger than 1, choose the closest pair. It could be, the closest pair could be 1 point and another point. It could be 1 cluster and another cluster. It could be 1 cluster and 1 point. Whatever, you merge the two. That gives you the bigger cluster. And then you keep on going. Okay, and when you merge the two, you sort of delete the component clusters from the current list of clusters, and then you include the new cluster, whatever representation of the new cluster you want to have, right? And then you keep on going until the number of clusters is 1. As we said, that this is again a religion. I mean, you could choose the you could choose the distance of a now in general we are now defining the distance between two clusters. Right? One of the clusters could be containing 1 point, and another cluster is potentially containing more than 1 point. How do I define the distance between 2 points? One that we were saying, one of them is what we are saying is called the closest pair, in which you say that the distance between cluster C1 and C2 is given by the distance between 2 and 3, the point 2 and the point 3. No, distance between two clusters is given between point 1. I mean one of the elements in one cluster and the other element in the other cluster, and the minimum distance between them. So formally defining that the D closest pair between C1 and C2 is defined as min of x belongs to C1, y belongs to C2, d of xy. Okay? So this is the closest pair distance. And we could be running the entire clustering with this. Right? And this would be called a single link clustering. We could also be defining a farthest pair. Right? I could be saying that, okay, no, look at point 1, look at the pair point 1 and 6. I mean, this is the farthest pair, where one element of the pair comes from cluster C1, another element comes from cluster C2. What is the intuition here? Intuition here is that I want to make the entire cluster cohesive. So even if one of the distances is big, I should call the distance between two clusters to be big. So that's the intuition, right? So then I say that the distance between the farthest pair distance between cluster C1 and C2 is defined as what? Max of x belongs to C1, y belongs to C2, d of xy. Okay? I could define it to be the average of all the distances, which may be a little more robust. Then I'll take all the pairwise distances, right? And I'll define the average. The d average of C1 and C2 will be defined as average of x belongs to C1, y belongs to C2, d of xy. Average of these numbers. Okay?
Do we need to find distributing all the points and then the minimum distribution?
Yes. Yes. We'll see how the complexity of this. We could also do that. That's another. I didn't cover that here. You could also say that a cluster is represented only using the centroids, and we find the distance between two centroids. That's yet another method that I think is called Word's method. I don't remember that exactly. I think it is called Word's method. I've forgotten, but that's a valid method of doing it. Okay? Any other questions? So once you have defined this way of measuring, see, here the only missing piece in the previous algorithm was this: how do I measure the distance between two clusters? And once you've defined it, the algorithm is done. It's very concrete, right? Because I always take the closest pair according to whatever definition of closest pair, and then I keep on merging. Okay. Okay. So, yes.
When to choose the closest pair, when is the farthest pair?
Or when to choose the closest pair, when is the farthest pair? Again, frankly, I don't have very good guidelines on this, right? There are some intuitions. What is the significance of one over the other? So in fact, the closest pair has a very nice significance. Closest pair, I'll sort of tell you, the closest pair has a very nice significance in terms of, we'll look at. Have you guys done minimum spanning tree? So I'll claim that the closest pair is really giving you the minimum spanning tree. If you think of the points, if you think of the graph, see, in minimum spanning tree, we're given a graph. right? And we're given weights on the edges. So imagine, what is the graph here? There's no graph. But imagine that the points are, imagine that the original points are in 2 dimensions. Imagine this, right? And then imagine the graph between them as basically draw a straight line between any 2 points, and the weight is the distance between, the Euclidean distance between these 2 points. Okay? Or some in our higher dimension, the points are drawn in higher dimension. Basically, it's a complete graph with the weight of the edges to be the Euclidean distance between these 2 graphs. It is not very hard to show that when you're running the single link clustering, you're exactly considering creating the minimum spanning tree of this weighted graph. And it has some nice properties, right? But what it can have is that it might be that look, what might happen? I mean, C1 and C2, maybe C1 and C2 are close, have been sort of defined close because there is one point here that is very close to one point here. But maybe other points here are very far from other points here. So in that sense, that the clusters are not that spherical in single link clustering. Huh? Yeah, basically. I mean, everything in machine learning depends on business logic. Everything that you're not sort of, once you have formulated the mathematical, everything in science is business. It depends on how you're going to use it, what you're going to use it for, right? I mean, we think the science is objective, it's clearly not. Okay, so where was I? So then we have these 3, these 3 and a few more, and we'll also experiment a little bit with hierarchical clustering today in the lab section, and we'll see what are other possibilities. But let us look a little bit into single link clustering because I mentioned it. So here are 2 pictures, and 3 pictures, and these are, you don't get much from these pictures. I just want you to see that, and these are pictures I think on some tumor physiological data, and then these are 3 clusterings performed based on average, farthest, and nearest. And you see that the structure of the trees tend to be a little different. Right? So the nearest is, I would call the average to be more balanced, more sort of nicely spread out, right? Which is what we intuitively think a clustering should be. Nearest is more everything is on one side, and then it's kind of building together, right? So the average might be the nicer thing to look for if you're interested in all nice and spherical clusters. But again, I have no way of really making this formal. Okay. So is there any principle, right? It would be nice to have an objective function, right? And what is the complexity? Let's answer the second question first, the easier question. What is the complexity? Let's say you have the single link clustering, in which you're taking the closest pair. What is the complexity of that? So how many, okay, again, faced with this question, always break it down. How many times are we doing cluster merges? Is it logarithmic? I'm hearing an answer logarithmic. But how many times are we doing cluster merges? Merging 2 clusters. We could be doing it? Potentially, we could be doing it log n times, but it could also be as bad as n. Because it's possible that I'm building a cluster by adding one thing to it. So potentially it could be as bad as n. In what you kind of see here is sort of like it's very skewed. It's growing one by one point. Ideally I would really like it that initially 2 points, and then clusters become of size 2. All clusters become of size 2. Then all clusters become of size 4. In that case, it would have been much less, but potentially not. So then there are n possible merges. For each merge, what do you need to do? Find the closest. Decide that you have to select which pair to merge. How long does that take? It kind of takes order n square, right? Because there are n square pairs. You have to select which of these pairs. So each time to choose the closest pair, it takes time n square. And then there are n merges. It's about n cube. It's not very good, right? N cube. So again, the same question will come. Can we parallelize this? This seems a little trickier. We'll see. Actually, one nice thing about single linkage clustering is that it's kind of canonical in the sense that if you take a reasonable data set, I mean, you take some of these data sets that people claim clustering is hard on, would this work for single linkage? Would single linkage give a good clustering here? Yes? No? Closest pair. It would totally give a good clustering here, right? Because what would happen is that one cluster would go along this periphery because of the closest pair. Another cluster would grow along here. Third cluster would grow along here, and they get merged only at the end. So this would totally work here. So that's a very nice thing about single linkage. That it sort of, there's nothing about, say, I mean, again, then what I would say is that if you don't know much about the structure, if your structure of the data is convoluted in this high dimension, single linkage is a good thing to try, actually. And because it doesn't rely so much on a spherical notion of clustering, right? So actually, it's a little sort of, it's possible to kind of frame that in a little sort of more structured way. So imagine we have this new cost function for clustering, right? Because previously we saw the k-means cost function, but imagine we have this new cost function for clustering in which we say that, okay, you have given me a cluster of the points, right? But now what I do in order to measure the quality of the clustering, so the cost of this C1, C2, C3 is as follows. That first I look at the distance between any two clusters. I look at the distance between C1 and C2. And so remember what the distance between C1 and C2 is. It's the minimum distance of a point in C1 and a point in C2. Then I look at the distance between C2 and C3. Minimum distance between a point in C2 and a point in C3. Sorry, C2 and C3 is this. And then I look at the distance between C1 and C3, which is this. And then I take the minimum of the distances. Right? And this is something you want to maximize. We want to maximize. Right? So what does it mean? We want to make the clusters as different from each other. Right? That we want to make the clusters far away from each other. Sorry. Was there a question? We want to make the clusters far away from each other. And we're measuring far away by measuring the distance between two clusters by saying that, okay, even if you have one person that's very similar to one person that I have, we are same. We are close to each other. Right? That's one definition.
Why do we take minimum and then try to maximize it instead of
Directly taking?
maximum?
Maximum of what distances?
CI,
Because see, there are two things you have to do, right? Oh, acha. So you're saying that the cost K of C would be max of? But see, this is the definition of one clustering. Now you have to now you're searching over all possible clusterings. What will you do there? I mean, then what you could have said that then it makes sense to minimize this, right? Because max of max doesn't make sense. Either you minimize the maximum distance or maximize the minimum distance. I mean, this is not something that it has other nice properties, I'm sure, but this is something that we use. And my point is that if you have this particular objective function, this is very, very connected to the tree that we got in the single linkage clustering. That once you have created the tree, right? Okay, here is my statement. That suppose somebody tells you, okay, do pre-process what you want, but tomorrow I'm going to come and ask you that, okay, I'm going to give you 10 different Ks, and I want you to tell you, and I want you to tell me what is the optimum clustering according to each of these Ks, for each of these Ks, according to this clustering cost. Is the question clear? That you will be, you can do whatever you want, but tomorrow you'll be given 10 possible values of K. You don't know that a priori, which are the values of K. But you'll be asked to give 10 possible values of K, and you have to say that, okay, according to this clustering cost, what are the optimal clustering for this k equal to k1, k equal to k2, k equal to k3, k equal to k4, k equal to k5? What would you do? You can close enough. It can, you can show that what you should really be doing is creating only one of these trees, right? And then if you want to get the k clusters according to best k clusters according to it, you just remove the last k minus 1 edges that you have put in. Because if you remove the last k minus 1 edges that you have put in, you get k components of the tree. And those are exactly the optimal according to this cost. It's not very hard to show. You can go over the proof later. And those are exactly the optimum according to that cost, and therefore, this is nice in the sense that once you create one of these trees, you can then use it to answer a clustering cost for multiple k levels. So that's why this is nicely used. Okay. There are other sort of lots of other recent work going on here, and this is this is all very, very researchy. This is all in the last 2-3 years. If you look at if you want pointers, if you look at papers in KDD, www, you will see that how do I sort of as we say that this takes time n cube. Right? How can I parallelize this? Is it possible to parallelize this? It looks kind of impossible because we are joining two clusters, and then we're joining two clusters, and then we are doing something, right? It looks like we have to do it step by step, but turns out not. You can parallelize this in this MapReduce setting. So I have not defined you what MapReduce is, but basically it is that the idea is that the data is distributed across multiple machines. You do each machine does some computation, then it does some merging, and then it does some computation again. So this is one round, basically. Okay. So it's not very hard to show that a version of I don't know what algorithm have you guys have learned from MSc. You must have learned Prim and Kruskal. There is yet another algorithm that we don't tend to teach in undergraduate that is called Borufka's algorithm, right? And it's not hard to show that using Borufka's minimum spanning tree algorithm, you can do single linkage in logarithmic MapReduce rounds, which is already fairly nice. Right? Because logarithmic MapReduce, actually in theory it's logarithm, in practice it's log of the diameter or something. That is already fairly nice. But you can also show, and this was just a paper last year, that you can do it in constant number of MapReduce rounds, only 3, I think. Okay. Furthermore, there's also a very recent sort of line of work that shows how can we define an objective function for hierarchical clustering in the same way as we do for k-means, right? And how can I create this different clustering approximate this objective function? How can I do it when the points keep on changing and so on? So there's lots and lots of research work in here. Yeah.
So in MapReduce also, we're also doing it in stages also, right?
We're doing it in stages. So the stages are not as simple. So I showed you the MapReduce stages for k-means. MapReduce stages here are a little more complicated. But we can talk later, but we are doing it in stages, yes. So each round is a stage. Okay. Any other question? Okay. So basically, so this is where we'll sort of end now. What we did today was mainly clustering, and hopefully we have seen that it's a fairly rich area. Both from the point of view of theory and practice. There's been amazing work in terms of theory. The one tricky thing has been that there's been a disconnect in terms of the theory and practice, but that is slowly going away. We saw a lot of distance functions and their properties. And you wouldn't believe, and it's sort of, how many open questions are there even right now? In terms of these. We saw k-means objective function. We saw this very interesting k-means plus plus, and this k-means parallel. I think maybe I haven't given you the name, which is the MapReduce version of k-means. And we did do an introduction to hierarchical clustering, and the 3 different types of hierarchical clustering, although we didn't really go into the objective function and so on. So the next time we'll start with with dimension reduction and connection of clustering to dimension reduction. That's what we'll do. Okay. Okay. Thank you. Any questions? Okay.